So we're going to take a look at the colligative properties post-lab. So this was a two-part thing. Part one is determining the I value, and part two is essentially using cyclohexane and a known along with an unknown to kind of work your way through understanding the freezing point. Cyclohexane is great because it has a very high freezing point, so it's easy to do in the lab and it melts quickly. So with that said, let's get into it. So let's start with the discussion questions. Identify two changes you could make in part one that would cause a change in magnitude of the freezing point depression to increase. Okay, so whenever I end up with one of these problems, I always write down the equation that I'm using. Okay, so we're going to write down the full equation, delta T, delta TF, the change in freezing point is equal to the KF value times the molality times I. So before we continue, what I like to do is I like to analyze each of these things individually, decide which one I have control over and which one I don't. So we know that in this experiment, what would cause the magnitude of the freezing point depression to increase? So what would essentially increase the delta T? That's the question that we're asking. What is going to increase the delta T value? And in order to do that, essentially any one of these going up would increase it on the other side. So if I increased KF, that would increase delta T. Increasing molality would increase delta T. Increasing I would increase delta T. So we're just simply saying, hey, if I increase any of these, that would ultimately change delta T. But the question is, which do I actually have control over? Well, KF, that's constant. We are locked in at the value of water in this case, right? So we cannot change that KF. We experimentally determined it, but that's also locked in based on whatever substance you're using. So this is also constant. So the only thing that is going to change is molality. So how do I increase molality? All right. Well, we're looking for two reasons. Ultimately, what I want to do, and I'm just going to say in summary, really what I want to do is increase molality. Well, how do I actually increase molality? Well, we can actually break molality down into two things, right? Molality is actually, if we kind of look at it, moles of solute over kilograms of solvent. So that right there is what breaks down to molality. So if I wanted to increase molality, I have two choices when it comes to this fraction. I can increase the moles of solute, or I can decrease the kilograms of solvent. So again, what we're doing is we're simply saying, this is what I want to happen. I can't do it with KF. I can't do it with I can do it with molality. How can I change molality according to the experiment? So in the experiment, I can increase molality by increasing moles of solute, or I can increase molality by decreasing the kilograms of solvent. So whenever you run into one of these problems, your goal should essentially be, okay, let me look at the equation, let me see what values I have control over, and how would I adjust them to get what I'm looking for. But ultimately, in order to change KF, increase KF, I need to increase moles of the substance or decrease kilograms of the solvent, both of which would increase molality, giving you a higher delta T. All right, moving on. So let's move on to the next one in part 2A. So this, for part 2A, we were determining the pure freezing point of cyclohexane. So we were determining TF naught. That's what we were trying to determine. So suppose 10 mils of cyclohexane was added to the test tube instead of the 12. Would the change in volume have any impact on the freezing point, on the measured freezing point? Well, does the quantity of cyclohexane change the freezing point? No, no change. There is no delta. There is no change in freezing point. Why? Because freezing point is an intensive property. So freezing point is an intensive property. Ultimately, what that means is, sure, maybe with 10 mils, I would get there sooner, right? With 10 mils, I might freeze it quicker because there's less stuff to freeze. Um, but ultimately, it is an intensive property. So the quantity doesn't matter. If I had 10 mils or 100 mils, it's still going to freeze at the exact same point. Granted, the more we have, the more accurate the reading is going to be because it's going to take longer for all of that to freeze. So in general, that's what we're looking at, but ultimately it's not going to change the measured freezing point. That should be constant at that pressure. All right, moving on. So cyclohexane has a pressure of 98 torr at 25 degrees Celsius. This is pretty low. That's the point of this. And what that ultimately means is because it has a low vapor pressure, it really likes to essentially, when you open up cyclohexane, you get that whiff of it immediately. And so what that basically says is it likes to vaporize. So what this is ultimately saying, if the mass of cyclohexane decreased due to vaporization, hence the 98 torr, I don't really care about the actual vapor pressure, just the fact that it is going to decrease the amount present. We're going to lose some of it due to vaporization throughout the experiment. So, assuming no impact on delta T, explain how this impacts the Kf value determined in part 2b. So, in 2b, we determined Kf um, with a known solute and cyclohexane. I'll just put cyclo. So, again, let's go back to the equation. Delta TF is equal to Kf times molality times I. And so for this experiment, we have to decide how this impacts Kf. So really what I'm curious about is what happens to Kf. So I'm curious what happens to Kf. The equation will always tell us. What's constant? Well, we said that delta T has to remain constant. That's written right here. No impact on delta TF. We know that we're using the same known, right? So the I value has to remain constant. And so again, it comes down to molality. So let's rewrite this equation, removing the stuff that we need to. So delta T, we are still curious what happens with Kf. And again, we're going to split out molality into moles of my known in this case, divided by kilograms of cyclohexane. That's my solvent times I, but we can actually just ignore I because it doesn't matter. So in this case, think about what happens to Kf. Keep in mind delta T has got to stay the same, so it's got to stay constant. Well, if we're looking at this equation, we're saying that we are going to, because we have a low vapor pressure of cyclohexane, it will vaporize easily. That reduces the mass of cyclohexane. What that means is if I'm going to essentially decrease the amount of my, essentially, I'm decreasing the kilograms of solvent that I have. So what happens to molality if I am we can go back to the original question if we want to for that. So I'm decreasing kilograms of cyclohexane. Ultimately, what that means is molality is going to be going up. So molality goes up because we're losing some of the solvent, it's getting more concentrated. And so if molality goes up, remember, delta T has to be the same. KF actually has to decrease to compensate. Or we are really how I should say this is delta T is the same. If we lost some, if molality goes up unintentionally, we are going to perceive a lower KF value. So ultimately, what this leads to is a decrease in kilograms of cyclohexane. So if I decrease the quantity of cyclohexane, it increases molality, which is equal to, which ultimately leads to a decrease in, I'm going to say, perceived KF. So ultimately, we see a decrease in KF to compensate for that increase in molality. Molality goes up, KF has to go down in response in order to keep that delta T the same, in order to maintain that constant delta T. So we would have a artificially low KF in this case. So KF is going to be smaller than expected given that circumstance where delta TF would change. So all right. Decrease in perceived KF. Good. All right, moving on. So let's take a look at the next step, which is the post-lab problem. So we have this solution of uh, HClO2, which is uh, chloric acid. Um, so the chlorous acid is what we have, and it is a weak acid. Only 36% of the molecules dissociate when dissolved in water. And so the question is, calculate the Van Hoff factor for this HCl if 36% of it dissociates. Okay. So before we even do that, let's take a look at two examples. HCl has an I value of 2. So this equation right here, it dissociates completely. So another way to think about that is if we thought about percentages, but really if we thought about just an individual molecule, initially I have 100 HCl's and I have 0 H pluses and 0 Cl's. This is before any dissociation happens. And then I give it a second, give it time to dissociate, give it time to equilibrate, do what it needs to do, do what it needs to do. So after you give it a moment, I should have 0 HCl left because it completely dissociated. 100% of it's gone, dissociated. And what it turned into is I now have 100 H pluses and I have 100 Cl minuses. It 100% dissociated. So if I started with HCl, 100 HCl's. I now have 100 H's and 100 Cl's, but they're separate from one another. Overall, the question is, how many particles do I have? Well, in solution, that's what's left. I have 0 HCl and I have 100 each of the H plus and the Cl for a total of 200 particles. Remember, when it comes to colligative properties, I don't care about the type. All I care about is the number. So because I have 200 particles in solution, I have a I value equal to 2.00 in this case. Essentially, 100%, 100 of them to total dissociation gives me 200. I've doubled my particles. I've got 2. If we take a look at the next one, where I is equal to 1, HCN barely dissociates. It's essentially 0. We're going to do the same kind of thing. Initially and final. If you imagine this, HCN, I start with 100 HCN molecules. I have none of the H plus and CN to start. Well, none of it dissociates. So all of that HCN is still just simply HCN. None of it dissociated. So here we go. I still have 100 particles in solution. Again, the type doesn't matter. The I here is equal to 1. None of it dissociated. That's what I'm left with. So now the question is, well, what happens for the HClO2? So let me take this HClO2 and we're going to take a look over here to the side. Paste. There we go. All right. So if we imagine the same thing happens for my HClO2, again, initial, final. If I start with 100 HClO2s, zero of these, zero of these, 36% of it dissociates. So that means that 64% of it is going to stay in that form. That means 36 of them have dissociated. 36% have reacted and gone to products. The rest have stayed put. So 64 and 36 totals out to 100. So now I'm just going to sum up the total particles present. 64 plus 36 is 100, plus 36 gives me 136 total particles, HCN, H plus, and CN minus all in solution. So only 36% of it. So essentially what we end up is 1.36 is equal to our I value. So again, we can think about those individual particles as individual, 100, start with 100. Each one of percentages counts as one dissociation, and that's what you end up with. So our I value here is 1.36 because 36% of it dissociated. But remember, I can't be less than 1, or can it? We're about to find out. All right. So next up, calculate the freezing point of the 0.05 molal HClO2 solution. So we're going to do freezing point. All right, easy enough. Delta TF. Actually, let me do TF. So calculate the freezing point. That's what it is. And we are given, again, 0.05 molal HClO2. So delta TF is equal to KF times molality times I. KF is a constant, which we should know from above, 1.86 degrees C per molal. Molality is 0.0500, 3 sig figs. Molal times my I, 1.36. So molality cancels. I'm left with degree C, which makes sense because that's the delta T. 1.86 times 0.05 times 1.36 gives me a value of 1.126 degrees C. I have 3 sig figs in my molality, so I should have 3 sig figs in my answer. Great, we're done, right? Now it's asking for the actual freezing point. Keep in mind that the delta T is deviation from the freezing point. So if my new freezing point is going to equal the pure substance freezing point minus any delta T of that freezing point. So whatever my initial one, and then it's going to drop by the delta T, right? So water has 0 degrees Celsius minus the 0.126 degrees C for a value of negative 0.126 degrees C. Again, we usually just kind of ignore that because when we're using water, we just know it's negative, whatever our delta T is, but that's not always true. If we're using a different solvent like cyclohexane, for example, our starting point is like, 7.6 degrees or something like that. So we need to be aware of it. All right. So next up, calculate the osmotic pressure. Okay, so we're looking for osmotic pressure of the solution above, which is 0.05 molar barium chloride at 25 degrees Celsius. We have a density and we have a molar mass. So off we go. All right. So in order to calculate osmotic pressure, we need the equation. Pi is equal to, and this is important for osmotic pressure, it's molarity times R. There's a pressure, so this is going to be the 0.08206. Molarity times R times temperature times the I value. Okay. Do we have any of those? Yeah, we have R. Do we have molarity? We don't. We have molality. So let's briefly talk about how we transition from molality to molarity. You need the density in order to do this. Okay, so molarity to molality. Um, yeah, let me briefly think about this. Actually, let's pause for a moment. We do have to think about this in a little bit of a different way. We do need the density for this, but we have molality. Okay. We don't have a quantity. So we can kind of make an assumption here about how much we have. And it's 0.05 00 moles of barium chloride. And we have 1 kilogram of my solvent. In this case, the solvent is going to be this is molar mass is okay. Um, yeah, 1 kilogram of this solvent. Yeah, 1 kilogram of my water, right? Because it's in water. Okay. What I am looking for is molarity. Molarity is moles, in this case, of barium chloride. We already have that, right? We can just plug that number in, 0.0500 moles. But the problem is we need liters, right, of my solution. So in order to get liters of solution, I actually need to know how much total mass I have and then use the density to convert that. Okay, so keep that in mind when doing these calculations that when you're going from molarity to I'm sorry, molality to molarity or backwards, keep in mind that we have to adjust on the fly here. So I have 1 kilogram of water, and actually, I'm just going to say I have 1,000 grams of water. How much barium chloride do I have? Well, I know that I have 0.0500 moles times fraction. I want moles to go away. I want grams to remain. 1 mole, 208.2 grams. So 208 point, so zero point zero 0.05. 0.05 times 208.2 gives me 10.3 sig figs grams of barium chloride. This is not going to make much of a difference. 1,000 is massive. We'll see. It doesn't really make much of a difference. 10.4 grams of barium chloride. So my total solution is 1,010.4 grams of solution. Now I can take this and I can use the density in order to do this conversion. So grams of solution to milliliters in this case, because it is going to be in mils. So 1.05 grams to 1 mil, divide by 1.05, gives me, grams cancel. I am left with, let's see, 1,000 and, is it 1,010.4 divided by 1.05 gives me 962 milliliters, or I could just simply say 0.962 liters. So now I can plug this in 0.962 liters divided by 0.05. Okay. So we end up with a molarity of, one more time, so 0.96, 0.05 divided by 0.962 liters gives me, uh, sorry, one more time, 0.05 divided by 0.962 liters gives me a value of 0.05 molar. Okay. Now that we have this, we've got everything that we need in order to solve this. So molarity 0.0520 molar. My R is, zoom in on this, 0.08206 liters times atmospheres, moles times K. My temperature, well, again, it's at 25 degrees Celsius. So 273 plus 25 gives me 298 Kelvin. Always has to be in Kelvin. It has to match the units of R, 298 Kelvin. Don't mess the I value up. Barium chloride, it dissociates into three particles. It is going to fully dissociate. And now we just simply do the math times 0.08206. I'm going to write the number down and then we'll deal with units. Times 298 times 3 gives me a vapor pressure, or I'm sorry, osmotic pressure of 3.81. Now, units. Kelvin goes away. Moles per liter goes away, leaving behind atmospheres. All right, I had to do that one on the fly because I realized I made a mistake. So it happens. There we go. So 3.81 atmospheres. It's a long way around, but you kind of work your way through it. Moving from, it's really important that you don't mess up kilograms of solvent versus volume of solution. Okay. Again, plenty of people mess that up. I don't want you to. And always think about the I value whenever you're given a problem. Always think about the I value too, because it's not always one. It's going to be different. Speaking of I value, let's take a look at this last one. Okay, so in this example here, we've got a lot going on. So students essentially did the same exact thing that you all did. Okay, so Chem 152 student determines the freezing point. Okay, so we have a solvent, ethylene dibromide, and that's step one. So they determined the TF naught, the pure substance freezing point, to be 9.79 degrees Celsius. Okay, great. The student dissolves 1.23 grams of benzoic acid. Okay, so that's the solute that they put into solution, and 23.482 grams of ethylene dibromide. Again, that's our solvent. So let me just tag that. This right here is the mass of our solute, or solvent rather. Okay. They measure the freezing point of the solution, freezing point of a solution to be 7.69 degrees C. So this is the TF, not. This is the new solution, 7.69 degrees C. The molal freezing point, so the KF for the solvent is 11.8. So this is KF is equal to 11.8 degrees C per molal. Great. So now we can start to solve the problem. So question 3A, assume the Van Hoff factor is exactly 1. Okay, I is equal to 1, easy enough. So I equals 1. Moving forward, calculate the experimental value for molar mass. So what is the molar mass of benzoic acid based upon the measurements above? Okay, so again, let's start from the end. What I am looking for is molar mass of my benzoic acid. I'm going to call that BA in the future, BA. So the molar mass of benzoic acid, which is going to be moles of benzoic acid over, I'm sorry, grams per mole. So grams of benzoic acid over moles of benzoic acid. Do I have either of those? I actually do. I already know that I have 1.23 grams of benzoic acid. So that was my sample size, 1.23 grams of benzoic acid. So in order to get my answer, all I simply have to do is determine the moles. Okay, well, it's probably going to be in the delta T, and it will be in the delta T. So let's figure it out. Okay, so I said I equals 1. So delta TF is equal to KF times molality times I. Okay. So I know my delta TF is the difference between the pure substance freezing point, 9.79 degrees C, minus the 7.69 degrees C. All right. My KF was locked in at 11.8 degrees C per molal. My molality is what we're looking for, actually. So we're going to look for molality because that's the only thing we don't have, and we know that I is equal to 1. So let me rearrange and write this out. So if I do the delta T, 2.10 degrees C is equal to 11.8 degrees C per molal times molality, and we can just ignore I. If I solve for just divide both sides by 11.8 degrees C, right? You end up with a molality of 0.178 molal. Hidden within molality, as it always seems to be, we know that 0.178 molality is equal to moles of benzoic acid over kilograms of solvent. And we are lucky we have kilograms of solvent, 0.023482. I get that from this. Oh, I'll do that. There we go. I get that from the 23.482 grams of ethylene dibromide. It's point, move the decimal, divide by 1,000, however you want to look at it. So I can now solve this. Once I have figured out the molality, I can now solve for moles of benzoic acid. Moles of benzoic acid is 0.00418 moles. Again, I'm just going to cross multiply that, and it's going to leave behind moles of benzoic acid, which I can now plug in to my equation or my initial question 418. I end up with a 245 grams per mole, rounded properly. There we go. 3 sig figs for my answer. That's generally what 245 grams per mole. So that is the experimental value for molar mass of benzoic acid. Okay, good. Moving on to the next part of this. We're going to come back to this one, or we're going to remember that. Calculate the theoretical molar mass of benzoic acid. All right, well, calculating the theoretical molar mass of benzoic acid is easy enough for us to do. We're just simply going to determine the molar mass of it. So just doing the mass of C6H7O2, we determined that the benzoic acid should weigh 122.121 grams per mole. Okay. Use that theoretical. So now that we've done that, use that theoretical molar mass to calculate the experimental. I guess I'll do it using that theoretical molar mass. Second question here, calculate the experimental Van Hoff factor based on the measurements above. Okay, so we want to know the Van Hoff factor. Again, delta TF is equal to KF times molality times I. Okay, so my delta TF 2.10 degrees Celsius, my KF 11.8 degrees C per molal. What is my molality? Okay, well, my molality is a little bit different here. Okay, so we're going to figure out what molality is and then plug it in. But we need to really figure out what I is. So let's just come back to molality because that's what we need to plug in. So molality is going to be my moles. Again, molality is equal to moles of benzoic acid all over the kilograms of solvent. Well, I know that I have 0.023482 kilograms of solvent. And how much benzoic acid? Well, remember, we measured out 1.023 grams of benzoic acid, which we had above. So I'm just going to show you again. Again, 1.023 grams of benzoic acid. That's where I'm getting that number. But because I don't have to find it some fancy way, because I now know the molar mass of benzoic acid, I want grams to go away. I want moles to remain. 1 mole of benzoic acid is 122.121 grams. Grams of benzoic acid cancel, leaving behind 0.008377 moles. Now I can plug that in 0.008377 moles. That's a 7. There we go. I end up with 0.3567 molal. Now that I have that, I can plug that in. So we're given the solvent, we're given the quantity, so we can actually measure this out. 0.3567 molal times my I value, but that's what I'm looking for. So I'm going to divide by 11.8 both sides, and I'm going to do the same thing to the molality to get rid of them on this side and leave behind I. I is equal to 0.499. Essentially, I is equal to zero point 0.5. How is that possible? I thought it was impossible to be below 1. No, this is correct. You got the answer right if you got this. Um, you got the answer right. So the question is why? How is it possible to have something less than 1? Well, this must mean that something special is happening, and it always happens with these substances. So here's my benzoic acid molecule. I don't really care about, uh, I really don't care about any of this. This is not the important part. So we're going to call this R. It's what we typically do, but we don't really care about that portion of it. What we care about is this. This little portion, the carboxylic acid, is going to be important. So what happens is if I just had a single benzoic acid, in fact, maybe I will not call it R in this case, I'm just going to call it. So if I write this out, there is my double bond oxygen, carbonyl, and here's my oxygen, here's my OH. So there's the carboxylic acid group, and I have a benzoic acid, which is a benzene ring. Right now, my I value is 1, right? So every single particle would be a value of 1. But something special happens uh, with these, okay? What happens is this happens with pretty much all acids too, by the way. Another benzoic acid is going to line up with it, and it's going to create this interaction between that pair of electrons and the hydrogen, and also this pair of electrons and the hydrogen. It's going to form a hydrogen bond twice. I mean, they're going to fit together kind of perfectly where we have that interaction. So this interaction kind of locks those things together and we form a ring between the two of them. Ultimately, what this does is that hydrogen bond makes those two so they lock in together and form what's known as uh, a dimer. So those two things coming together, it was one particle, right? So I have two particles here, but when they lock in together, so my I goes from 1 to 0.5 because now I have half the number of particles. Essentially, those two particles together, they act as one particle. There we go. So those dimers act as one particle. And again, I don't care about the type. I just care about the number. So every single benzoic acid finds a partner. And because they find a partner, they just act as one. So yeah, that's the answer. All right. Hope this helped. Feel free to come to me or any of your teachers for help. All right. Good luck.